Welcome to the TI Precision Lab series on light sensors. My name is Alex Bandari-Young, and I'm an applications engineer at Texas Instruments. In previous videos, we have discussed light sensors in the typical top-firing sensor configuration. In this video, we will be discussing the benefits and considerations of using a bottom-facing sensor. Most of the time when we picture a light sensor, we assume that the active sensing area and the solder pins are on opposite sides of the part, with the device facing up towards the ambient light. This is in fact how most light sensors are arranged and is referred to as a top-facing sensor. However, there is another style of light sensor where the active sensing area is on the same side of the package as the solder pin. This is called a bottom-facing sensor. For a bottom-facing package to receive ambient light on the sensor area, a cutout in the PCB is needed. This cutout will act as a new aperture, limiting the field of view of the sensor. To ensure a good field of view performance and the PCB assembly is manufacturable, special attention needs to be paid to the PCB cutout. With the additional requirements of bottom-facing sensors, why would anyone use them? In many applications where light sensors are used, such as smartwatches, phones, and laptops, the consumer desires the product to be as small and as thin as possible with the richest feature set. However, manufacturers are running into fundamental limitations on how small and thin electronic assemblies can get with traditional surface mount components. A standard surface mount package requires the wafer to be bonded to the top of a substrate. Bond wires are then connected between the pads on the wafer and the package pins. The device is also encapsulated in a mold compound. All these layers combine to set the minimum size and thickness the sensor and any assembly containing it can be. One of the ways to get past these size limitations is by using wafer scale packaging. Wafer scale packaging eliminates the need for a substrate, package pins, and a mold compound layer by using the wafer itself as the package. Instead of requiring separate package pins, wafer scale packages have a solder interface directly on the wafer pads. Since these solder pads are now on the same side as the sensor area, the sensor is bottom-facing. Wafer scale package sensors, like the TI OPT 3006 and OPT 3007 ambient light sensors, are thinner and smaller compared to a traditional package. For example, the OPT 3007 has a length and width of less than 1 mm and a thickness of just 0.23 mm. So the reason to use a bottom-facing sensor is clear. It will allow for a more compact design compared to a typically top-facing light sensor. While bottom-facing sensors can be very small, they require the addition of the PCB cutout for the sensor to receive light. This PCB cutout aperture will limit the sensor's field of view, just like an enclosure window, as shown. The field of view for this new PCB aperture will increase as the cutout area increases and as the PCB thickness decreases. Rigid PCBs have a typical thickness of around 1.6 mm, which greatly limits the field of view. Also, the cutout area is constrained by the need for solder pads on the PCB to mount the sensor. PCB manufacturers require spacing between pin pads and the cutout edge to ensure manufacturability. A typical spacing requirement for the solder pad to cutout edge is 0.25 mm on rigid PCBs. This requirement would be unacceptable for many parts, as it would leave little to no room for a cutout, given most bottom-facing sensors' small size. One way to get past this tight tolerance is to use a part like the OPT 3007, which eliminates the closest pins to the sensor area to allow for a less constrained cutout size. However, even with the OPT 3007's improved spacing, the PCB aperture alone would limit the field of view to below 10 degrees with a 1.6 mm thick PCB and a 0.25 mm pin to cutout spacing. As mentioned before, increasing the cutout area in the PCB will increase the field of view. The theoretically best shape for a cutout would be a rectangle the same aspect ratio as the sensor area. However, Due to the required PCB solder pad locations, the cutout cannot increase evenly in every direction. As an example, both the TI OPT 3006 and the OPT 3007 pinout allow the cutout to grow in the direction parallel to the pins. However, due to the no connect pins on the OPT 3007, no pad is needed on the PCB for the middle pins, so the cutout can also grow in that direction. That means the OPT 3006 has a maximum field of view when its cutout is the shape of a tall rectangle, and the OPT 3007 cutout is maximized by using a cross-shaped cutout, as shown in the displayed pictures. Using a flexible PCB instead of a rigid PCB can also help increase the field of view. Flex PCBs can be made much thinner than rigid PCBs, with typical minimum thicknesses of around 0.1 mm. Additionally, flex PCBs can typically achieve lower solder pad to cutout spacing than rigid PCBs because of the processes used to make these cutouts being more precise. Two common cutout methods for flex PCBs are laser cut and die punch. Laser cutouts are more precise and expensive typically. They also provide the most flexibility in what shape the cutout can be. With a die punch, the cutout is made by stamping it into the flex PCB. Die punched cutouts are typically limited to simple shapes like rounded rectangles or circles. Spacing requirements and cutout capabilities will vary from one flex PCB manufacturer to another, and these issues should be discussed with the PCB manufacturer before starting the layout of the PCB. Another consideration for a bottom-facing sensor is the alignment tolerance of the part to the center of the cutout of the PCB. If the sensor area is off-center from the cutout, the field of view may be significantly decreased, as it will effectively reduce the aperture size by the amount of offset. Modern pick-and-place machines can be accurate to 0.01 mm when placing the part, but the solder reflow process can cause parts to move significantly more than the placement tolerance. In practice, component positioning errors will increase for many reasons, so it is best to discuss sensor positioning requirements and recommendations with the PCB assembler before starting PCB layout. We have discussed the benefits and complications of a bottom-facing sensor, so now let's compare a typical bottom-facing light sensor, like the OPT 3007, to a typical top-facing sensor, like the OPT 3004. A bottom-facing sensor in a wafer-scale package will be much smaller and thinner than a traditional surface mount package. The OPT 3007 has 1/5 the footprint area and 1/3 the thickness of the OPT 3004. Bottom-facing sensors will require a PCB cutout that needs special attention to ensure the PCB is manufacturable and will give a reasonable field of view. A top-facing sensor does not require any cutout. In addition, most bottom-facing sensors, like the OPT 3007, will require placement on a thin flex PCB to achieve an acceptable field of view. A top-facing sensor can use a standard rigid PCB. Due to the PCB cutout aperture being so small, a bottom-facing sensor will be significantly more sensitive to PCB assembly issues than a top-facing sensor. In many applications where part size is not the most critical requirement, the typical top-facing sensor can give good performance with fewer restrictions. In applications like smartwatches, where size is tightly constrained and a flex PCB is likely already used, bottom-facing sensors can be a better fit. To find more light sensor technical resources and to search TI products, please visit the link shown. Thanks for taking the time to watch this video. Please try the following quiz. Which of the following will not affect the field of view of a bottom-facing sensor? The correct answer is C. While it is often desirable for components to be thin, it has no effect on the field of view of the sensor.